Okay, so I think we are very much on time, and I think we can start. So yeah, we are very happy to have the speakers of the plenary session in the afternoon of the second day of the conference. So the first speaker is Silvia Galli from IAPE, and she's going to talk about status of the cosmological tensions. So go ahead, Silvia. Thank you.
Yes. Hello, everybody, and let me thank the organizers for inviting me to give this talk. Unfortunately, I cannot be in Korea, so I chose to be in a tropical island, as you can see in my background. And I'm going to talk about status of cosmological tensions, in particular of the H0 tension. I'm sure that in the audience there are many of you that are not cosmologists, so I'm trying to I'll try to review a little bit why the cosmology community is so excited about this, and try to give you an update about where we are. So these cosmological tensions are sourced or started because of very precise measurements of the cosmic microwave background from the Planck satellite. As many of you know, the CMB is this radiation that we observe from the very early universe at the redshift of around 1100 from the last scattering surface. What's so special about this epoch is that before then, the universe was essentially completely ionized with photons that were not able to travel long distances in the universe because they were scattering very often off free electrons. And when the universe cools to a temperature of about 3000 Kelvin, protons and electrons recombine into neutral hydrogen, and photons are then free to propagate long distances, and so long that they are able to arrive until now, until us. And what's very rich about the cosmic microwave background is that it provides information really about the whole universe story, history of the universe, starting from, the seeds that of the density perturbations that created the structures that we see today in the universe. So set potentially by inflation, the physics of the photobaryonic fluid in how this recombines into neutral hydrogen, and also information about the later stages of the evolution of the universe, in particular scattering of electrons that are freed during the reionization of the universe, or also CMB photons are distorted by the large-scale structure of the universe through gravitational lensing. And we observe these, the CMB at an average temperature of 2.7 Kelvin, but what we really use for cosmology these days are the anisotropies of this temperature field, the small differences in temperature in different parts or directions in the sky that are distributed as a Gaussian random field. And all of the cosmological information is encoded in the 2-point correlation function of these anisotropies, or as we usually do, we look at these correlations in spherical harmonic space. So what we do is that we have these maps of anisotropies, we decompose them in spherical harmonics. These are like Fourier transforms on a sphere. We take the coefficients of these decomposition, and we calculate basically the variance of these coefficients. And these are the power spectra that you see all the time from for the CMB here multiplied by essentially L squared. And where you can see a lot of features that are linked to the physics of the CMB and that provide a lot of information, as I said, about cosmological parameters. The CMB is also polarized. 10% of the CMB photons are polarized, and is also extremely rich of information, and it's complementary to the information that we get from the intensity one. Now, the best measurements of the cosmic microwave background come from the Planck Satellite, which was an ESA satellite that operated between 2009 and 2013. And we had our last data release a couple of years ago with the last papers that came out actually very recently, last year. We had 3 data releases, and the final release used information from temperature and polarization to measure the cosmic, to measure cosmological parameters from the CMB. And the product of this experiment were these beautiful power spectra, the temperature one, the cross correlation between temperature and what is called the E-mode polarization. This is a specific polarization pattern in the sky, and the autocorrelation of the E-mode polarization spectra. And we also use in the cosmological analysis the reconstruction of the gravitational lensing. As I said, the CMB gets distorted by gravitational lensing, and which leaves a non-Gaussian signature in the maps that can be reconstructed in order to actually measure these the amplitude of this effect at different scales. And this is also, of course, precious cosmological information that we use to set constraints on cosmological parameters. Planck has provided or reached the goal that was designed for, which was providing the ultimate temperature measurements of the cosmic microwave background on the full sky. Then it's never on the full sky because we have the galaxy, so it's a percentage of the sky. But this is essentially the best you can do on the intensity power spectra. On the other hand, polarization, it's a much smaller signal. And Planck provided extremely good measurements on the cross correlation and the autocorrelation EE mode spectra. But you can see even by eye, for example, here that the error bars are large. So the information in the CMB is not exhausted. There is still a lot of information to look after in the CMB at high multiples, so small angular scales in polarization. And this is the goal of many ground-based experiments that are going on, and I'm going to mention a couple at the end of this talk. So the power spectra of the CMB are, as I said, are sensitive to cosmological parameters, and the most standard one is the lambda CDM one, which is uses six parameters, 6 cosmological parameters to fit the data. A couple of them to model the spectrum of the primordial perturbations. One that essentially regulates the typical scale of these of the anisotropies, the angular scale of the sound horizon, which essentially tells you how far the photobaryonic fluid could travel until the last scattering surface. One parameter that tells you when the reionization of the universe happened, and a couple of them that tells you how the physical density of baryons, so ordinary matter, and physical density of dark matter. And through the effects of these parameters that are different on the power spectra, one can measure these parameters. And these are the baseline results from Planck on lambda CDM, where the first 6 parameters are these 6 lambda CDM parameters, and these are some derived parameters. Starting having a model and having these measurements on these parameters, you can infer a lot of other quantities that are indirect measurements of these quantities. And Planck actually entered this era of sub-percent measurements of most of these cosmological parameters. They are extremely precise. You can see it in the last column here. And Of course, once we have such precise measurements, one of the key things is to be able to compare with other cosmological probes and see whether there is consistency across different cosmological probes. Different cosmological probes, you know, at different redshifts, using different techniques, will be sensitive to cosmological parameters in different way, and consistency will tell you whether the model that we use is actually a good model to describe the universe. Some of these, many of these comparisons with other cosmological probes are work extremely well with Planck, but one that started all this issue of mainly of cosmological tensions is the measurement of the Hubble constant. The Hubble constant is the expansion rate of the universe. Planck measures it at a level of 67.4 kilometers per second per megaparsec, with an error bar, which is the best to date, the best determination of the Hubble constant to date, with a measurement which is 0.8%. And the key thing that we hear over and over again is that this measurement is model dependent, in the sense that the CMB is not directly sensitive to the expansion rate of the universe today, but through the lambda CDM model, you can measure the Hubble constant. And the way you do it is essentially the fact that the Hubble constant, the expansion rate of the universe, enters the equations to measure distances. Distances are a key quantity that are measured in astronomy and in cosmology in particular, because they are linked to cosmological parameters. So if you are able to measure in some way distances at different redshifts, you are able to do cosmology. And the CMB allows you to do this, because the CMB measures this angular scale of the sound horizon that we indicate here with theta. And so if you are able to measure the physical distance of this sound horizon, you are able to infer a distance to the last scattering surface. And the CMB provides you also this, the calibration of this ruler, because through a model, we are able, through the lambda CDM model, we are able to measure this RS, which is the physical dimension of the sound horizon, which depends on cosmological parameters that you measure from the CMB power spectra. So these procedures allows you to measure H naught, but you can see that the model enters a lot. You need to know how to calculate this ruler, and you need to know how to measure this angular distance to the sound horizon and link it to the expansion rate of the universe. And here is where all the interest for this cosmological tension rises. So this is the measurement of the Planck CMB from the Planck CMB measurements. And as I said, the comparison with the best measurement of best direct measurement of H naught is pretty weird, which is shown here. This is the latest measurement from the Hughes program. Where Supernovae 1A, we calibrated with the Cepheids are used in order to set a direct measurement or to set the direct constraint on the Hubble constant. This is in nature a very different measurement from the CMB, because it doesn't depend on the cosmological model nearly as much as the Planck CMB is essentially independent on the cosmological model that you use. Supernovae are standard candles, which means that they are star explosions of basically white dwarfs accreting from a binary companion. And the key thing is that when they explode, their peak luminosity is always the same, or more precisely can be standardized. And the advantage of this is that, of course, if you know that a source always have the same peak luminosity, you know that the more this will far from you, the dimmer it will appear. So you can measure the apparent magnitudes of supernovae. If you know the absolute magnitude of the supernovae, you are able to infer distances. And as I said, distances are linked to H naught. And in particular, if these supernovae are particularly local, the distance essentially depends only on H naught. The problem with this is that you don't know, in principle, the absolute magnitude of the supernovae, so you need to calibrate them, which means that essentially you need to have some supernovae in galaxies where you are able to measure distances in some other way, and so you can infer the absolute magnitude of the supernovae. And this is done with galaxies that contain Cepheids, which are variable stars, that have a relation between their variation of their period of variation and their luminosity. So if you measure, you know, the period of these of the Cepheids, you also measure their their absolute luminosity, and so by observing their apparent magnitude, you can infer distances. The problem is that, again, these Cepheids, this relation between period and luminosity needs to be calibrated. So you need to have Cepheids in galaxies where you are able to measure the distances in some other way. And this is, the good thing is that you find Cepheids, for example, in the Milky Way, in the Large Magellanic Cloud, which is a close-by galaxy, or in some other close-by galaxies where you have other methods that work at very short distances, such as parallaxes. And this is exactly the method that you use in these distance ladder measurements, where you have the supernovae very far away, well within the Hubble flow. You calibrate the supernovae magnitude with galaxies that contains both supernovae, contain the supernovae and contain Cepheids at intermediate distances. And then you calibrate the Cepheids very close by in galaxies where you have other ways of measuring the distances. But you can see that it's a very convolved, it's a direct measurement of H naught, but it implies different steps and working with astrophysical objects, which is not always trivial. Let me say that there are alternative ways to calibrate the supernovae. For example, instead of using the Cepheids, is using this tip of the red giants branch, which I'm not going to describe in detail, but it's important for something that I'm going to say in the next slides. So this tension has been with us since 2013. At the beginning was the difference, between the first Planck release and the value of H naught from the Hughes group in 2011. At the time, it was even possible that this was a statistical fluctuation, and then the importance of this increased with time till now, which is at the level of 4 sigma. And the cool thing about all this time, that we spent on this problem, it's almost, 8 years. It's the fact that today we have many more measurements and on this problem. And so in some way, we start having much more information about the tension. So one information we have is about these the Planck measurements and confirmations of this measurement. There are in particular, one other way of measuring distances in a way which is similar to the idea of the one from Planck, which is from the baryon acoustic oscillations. The same characteristic scale of the sound horizon that we observe in the CMB, we also observe in galaxy distributions. And so by observing this characteristic angle, these are overdensities of baryons, essentially on a scale which is 150 megaparsec. we observe this characteristic scale. And so again, if we all have ways of calibrating this, so of knowing the physical scale of the sound horizon, which can be provided by the CMB, but you can also completely forget about the CMB and use some other data sets in order to inform the calculation of this physical distance. Essentially, you can infer a completely independent measurement of H0 from the CMB, which is also low, confirming that the CMB measurement. However, again, in a model-dependent way, BAOs are need to define a model such as the lambda CDM model in order to calculate all the quantities that go into the indirect measurement of H0. On the other hand, we have, as I was saying, other CMB experiments that are observing the CMB at high resolution in polarization in particular, the Atacama Cosmology Telescope and SPT, the South Pole Telescope. Both are, promised to do amazing things and provide very stringent cosmological parameters with their full survey. These are the first results from these experiments. And both these experiments provide values of H0 which are low, consistent with Planck, with error bars that for the moment are 3 times larger than Planck, but these are bound to shrink very rapidly in the next years. So we have multiple, so no one of these probes, neither BAO with other data sets nor the CMB ground-based experiments have each of them the sensitivity to have error bars that are as small as Planck for the moment, but they all indicate a low value of the Hubble constant. And on the other hand, there are also many measurements looking at the supernovae plus or checking the supernovae plus Cepheid measurement. And I want to highlight with relatively large error bars, but tending all or almost all to high values of H0. But I want to highlight 2 of them. One is this, the supernovae, but now calibrated with this tip of the red giant branch, which provides a value which is, first of all, with larger error bars compared to shoes and to the CMB measurements, and with a value which is in between the 2. So for the moment, this alternative way of calibrating the supernovae provided a measurement that is consistent with both sides of the story. And this will be very exciting in order to confirm or reject the validity of this Cepheids calibration for supernovae. And on the other hand, I wanted to highlight this other measurement, which is time delays of multiple image quasars. So the idea here is that you have a quasar whose image is multiply, you have multiple images from a quasar due to strong lensing provided by a foreground galaxy. And since the spectra of these quasars change with time, you are able to measure the time differences of the arrivals of these photons by simply looking at the features in the power in the spectra of these quasars, and these time differences depend on the distances, on the distance from the observer to the source, from the source to the lens, and from the lens to the observer in a combination of this. And the main point is, since these time delays are sensitive to distances, again, distances are sensitive to H0, and these are used in order to set a constraint on H0. And these, what, sorry?
5 minutes.
Oh, wow, I was super slow. Okay. And so just to say that these measurements were used to say, you know, that as a confirmation of the supernovae plus Cepheids measurement, but lately this has been disputed because essentially these measurements require a knowledge of the distribution of mass in the lenses of the foreground provided by these foreground galaxies. And if you relax some of the assumptions in the analysis, the error bars become much larger. So the problem right now, I think, is that we really need a second measurement as good as the supernovae plus Cepheid one that can confirm this late time measurement of H naught. So what is the problem in all of this you know, tension between early and late time probes? We don't know. There's a lot of debate about systematics in the distance ladder. It's 10 years that people have been looking at this, and there are still open debates, Cepheid crowdings, about the tip of the red giants, whether the reddening is done correctly, consistency of different anchors used for the calibration of the Cepheids, peculiar velocities and isotropy of the supernova sample, and these are still open debate in the community, and I will show you a couple of points here. And on the other hand, as well, for the CMB, you already see that there are multiple probes pointing towards the same values. And clearly the exciting idea here is that we could maybe, if this is real, there is new physics that could actually explain this, and what people mean by a solution works to explain the Hubble constant is always a little bit of a matter of taste, whether it reduces the tension from 4 sigma to whatever sigma. I think it's always a little bit unclear. I just wanted to mention this problem of systematics. There has been a couple of papers in the last year that showed essentially that the potential systematics in the H0 measurement from Shoes et al. However, this, for example, this paper came out a few months ago, and I think it will need a lot of scrutiny in order to understand whether what's claimed is potentially viable. They claim there is a difference in the dust extinction or in the relation between colors and luminosity of the Cepheids in the anchors and in the galaxies used to calibrate the supernovae. However, I think the critics to this paper is that this goes to very unphysical values, but this has the potential of moving down the value of H0. And also, as I was saying, there were critics about the consistency of some distances to in particular this galaxy that allows you essentially different measurements of distances from data sets used by Shoes, and there are discrepancies at the level of 2 to 3 sigma. So there are paths that we need to follow in order to first assess whether this is systematics or new physics. And clearly there is a whole part of the community that is working on new physics, and this is still you know, extremely hard. There was a lot of work to understand whether you can change how the universe evolves in the late time. So for example, how dark energy evolves in order to explain this discrepancy. The problem is that we have a lot of data in baryonic acoustic oscillations and supernovae. The uncalibrated supernovae actually provides information about relative distances, and so about how, for example, dark energy might evolve. And all of these data are setting very tight constraints on these late time solutions. And I will not going into the details, but there was also a very trivial mistake that some people were making when constraining these late time models. And I invite you to read this paper to clarify this, or I'll be happy to take questions about this. So another part of the community focused on early time solutions. So rather changing the way we calculate these physical dimension of the sound horizon. But I would say, and since I don't have time, I will just summarize this by saying that we are at the point where I think we don't have a physically motivated model that that fits all of the data that we have currently, and it is really able to provide a satisfactory solution to the H-snap tension. And I will just, well, I will skip this, and I would like just to mention that the future is bright, at least from the cosmic microwave background point of view. As I was saying, we have these amazing experiments, ACT, SPT, and in the future, Simon's Observatory and S4, that will massively improve our measurements of polarization at high resolution. These experiments have the potential of improving, our constraints by a factor of, well, for SPT3G in combination with Planck by a factor of 2. And then, for example, S4 alone is able to, improve lambda CDM parameters by more than a factor of well, a factor of 3 compared to Planck, and clearly to provide tests of cosmological models that are completely complementary from Planck. So the CMB is not done at all. There is still a lot of information to extract from the CMB, and these experiments are actually looking after these. And thank you very much for your attention.
So thank you so much, Sylvia. Interesting talk. Also, you finished pretty on time. So I think we are in a kind of a webinar thing, so people cannot really ask questions by voice. So people can put their questions in the Q&A session. So far, there are 3 questions from the regulars. These are the people who ask questions, I think, from every cosmology talk so far. So Owen is asking that, is there any understanding why local H0 is biased higher than Planck LCDM, even TRGB is higher? Then Sheikh Jabari is saying that it's going consensus that FLRW setup is just going beyond lambda CDM, is not going to resolve early versus local, which I think is connected to the next point, that is saying that there are some evidence for anisotropy in cosmic distances. So any comment on that?
Yeah, I acknowledge that one of these of the people asking questions actually wrote me a mail before the talk telling me that they would ask questions about this point, and which I found a little bit strange. I think
you can just give an honest answer.
Yes, no, absolutely. I think all of these are valid points. There have been a lot of papers, and I know that a part of them, I think Eowyn, for example, have been working a lot about, really understanding whether the Friedman, Lemaitre, Robertson-Walker, setup is valid or not, and trying to challenge even the knowledge of, for example, of isotropy, and really challenging even the knowledge of existence of dark energy. I've been looking at their papers. So for the first question, I don't know. The TRGB, I think, I think it's really. It's really dangerous, to say, there is something that it's 1 sigma high, and so this is high, I mean, that measurement has the potential of being 67 once the error bars shrink. It is suggestive, the fact that many other, for example, the ones from mega masers is also high with large error bars. I think you need to be, or at least from my point of view, from someone that has worked really, 10 years on systematics, each of those would need to go through the scrutiny that, the Planck and the Supernovae measurement have gone through in order to have the same, I would say, the same robustness in a way. You cannot imagine how many people have reanalyzed, this data. And so, I think all of these measurements are super important. We really need to be careful about, systematic error bars and whether these are, accounted for in the proper way. The fact that there is growing consensus that FLRW is not going to resolve early and local. I think there are papers that say this. And I think, demonstrating that setup doesn't work and ruling that out, I think, it would be an amazing discovery in cosmology, and we are all looking for, a big breakthrough in that. I think that's as big as demonstrating that dark energy exists, right? So we need super strong evidence that, that setup doesn't work. So far, it worked remarkably well. So I think, I am super curious and to see how, whether there will be mounting evidence, that's a possible way to go through. And I think that's my comment about that.
Yeah, thank you. I would add something that I think to test the isotropy, I mean, is actually a very tricky job, and one really need to understand the data. I think there are many analyses which they find something, but they don't consider larger scale velocity perturbations, which are important from the theory and observation part. And when one does that, then realize everything is fine. And I think this story goes back and forth every couple of years. We did some analysis 15 years ago and then 10 years ago, but again, people forget about that. They just get the distance moduluses and then do that. And then they thought, oh, we found. So yeah, as you said, this is certainly a very important issue, but to rule it out, one has to be really strong. So there's one more question from Jojun, said that there are also some self-inconsistencies between low L and high L from Planck for H0. Any comment on that? So.
Yes, this is story of my life for I don't know how many years. Absolutely. So we have this thing, right, that if you measure H0 from L smaller than say 1,000, you get something that is higher in H0, and then as you include the smaller L's, which in Planck has as much statistical power as the L's smaller than 1,000, then H0 shifts to lower values. Now we have been looking at this difference in all possible ways, and there is a Planck paper that I led together with Marius Milea, where we really asked ourselves, in simulations, how often you would see differences in the cosmological parameters that are as large as we see from high L and low L in Planck. And the answer is that this is, relevant at the 2 sigma level. Now, and this was done also by Graham Addison and other authors, and with the same conclusions. Now, we know that in Planck high L, there is also this other kind of weird thing, which is that the amount of smoothing of the peaks and the troughs is a little bit higher than what you would expect from lambda CDM, and this causes a lot of other correlated deviations in the Planck data. So there is something going on at high L. I would say, if you marginalize over this extra smoothing of the peaks and the troughs, you don't get H0 of 73, right? You can increase it a little bit. I don't remember if it's 68 or between 68 and 69, but you don't go to 73. So even if there is something there going on, new physics, systematics, whatever, and I can give an entire talk about that as well. It seems that this cannot be a solution to the H0 problem. So from a statistical point of view, this can be just a fluctuation, the difference between low and high L. I mean, consider you are, as I said, increasing your statistical power a lot. You are adding a lot of more data, and your posterior distributions are moving, and this is expected. This is just statistics, I guess. And we will have these ground-based experiments will go after the high multiples, both in temperature and polarization. So we will have ways of double checking that.
Thank you so much. So I think we have to prepare for the next talk. Thank you very much, Sylvia, for a very interesting talk. Hope to see you in person in Korea at some time. Yeah.
Thank you.
Okay, so hello, Ruth. So if you can share your screen, please.
Yes. Can you see my screen?
Yes. So, the next speaker is Ruth Durer. We are very happy to have Ruth again in one of our conferences in Korea, but unfortunately this time online. And yeah, so Ruth, I will give you a warning 5 minutes before end of the 30 minutes. So there is a 30 minutes and 5 minutes for Q&A. If you exceed slightly from 30 minutes, it's okay. Yeah.
Very good. Thank you very much. Good evening, everybody. I want to talk here about testing general relativity with cosmological observations.
But Ruth, your screen is dark. I mean, is it?
Oh. Sorry, you don't see my screen? Let me.
Okay, now we can see, yes.
Yeah, so maybe I can't go to full screen, then I have to stay this way. Okay. So the topic of my talk is testing general relativity with cosmological observations. Why is this? So first I will give an introduction, and then I will talk about very large galaxy surveys, because that's the way I want to argue we can test GR. I will talk about the angular power spectrum of galaxy surveys and the correlation function. And then I will mention three possible directions, namely measuring the lensing potential with large galaxy surveys, measuring the growth rate of perturbations, and then I will briefly talk about the so-called EG statistics. Okay, so why should we want to test GR? I mean, Einstein's theory of gravity has been tested in many ways and has passed all the tests with flying colors. We have seen light deflection, we have seen perihelion advance, not only of Mercury, but of many binary systems where it is several degrees and not just 50 arc seconds per century, but several degrees per year. We have measured Shapiro time delay, you name it. And since nearly 5 years now, we have also seen gravitational waves predicted by Einstein's theory of gravity. All these observations, however, they essentially test the vacuum solution to Einstein's equation, R mu nu equals 0. And can we also test Einstein's equation with matter, where we have a right-hand side which is non-zero? Is this possible? We know one solution which has occupied us for nearly 100 years now, which solves Einstein's equation with matter, and that's the cosmological solution, the Friedmann-Lemaitre universe, which is a very symmetrical, isotropic and homogeneous universe, which is described by a scale factor only and curvature. The geometry is described by scale factor and curvature of this metric gamma. And it contains a non-trivial right-hand side here, an energy density and a possible cosmological constant. That's the constraint equation. And then there is the dynamical equation, which is can also be derived from energy momentum conservation. Have we tested these equations in cosmology, with cosmological observations? What have we actually observed when we measure the dynamics of our universe? What we truly measure, not only, but mainly, for example, is the flux of, let's say, some supernova, which is related to its luminosity divided by the distance squared, luminosity distance squared, where in a Friedmann universe, we can express this luminosity distance as a function of the Hubble parameter, as you all know. And we have measured the so-called distance modulus, namely the absolute magnitude minus the observed magnitude from supernovae, the absolute magnitude through the calibration process, which Silvia just explained in the previous talk. So this vertical line here is proportional. This distance modulus is proportional to the log of the luminosity distance. And what this delta m minus capital M is actually the log of the measured distance divided by the distance which one would have in a Milne universe. A Milne universe is a universe with no matter in it, but just negative curvature. That's the zero line here. And the measurements are shown here. If we would have a universe which only would contain matter and no so-called dark energy, which never would accelerate, the curve would go along this red line, or if we would have a which always accelerates, which only has cosmological constant, the curve would be this red line. If we would have matter and curvature, we would be in this green region here, and the data is here. So with assuming a Friedmann universe, clearly this cannot be matter only, but it fits very well if we assume 70% of cosmological constant, this blue line, and about 30% of matter, which contributes to the expansion. But this is not a test of the equations which we mentioned before, right? We only measure the left-hand side, or the expansion of the scale factor A, and we infer from that that this must be the matter content, namely 70% cosmological constant and 30% matter, to fit this data. We haven't measured the energy momentum tensor at all, right? There are also 3 points here which are from the BAOs, which also have been mentioned by Silvia in the previous talk. So from these data, we actually have postulated the existence of dark matter and dark energy to fit the supernova data. This plot which I show you here is not the latest one. There is a later measurement with slightly more supernova. Here there are 1,000 and not just 700 as in the previous one. But the lesson is the same. To fit this, we need about 30% matter and about 70% cosmological constant, and we can get around with zero curvature. In this talk, I will show that if we use not only the background universe as was used for the analysis of this data, but we also use clustering observations, we can actually, namely the fact that the universe is not perfectly homogeneous and isotropic, but it has fluctuations on it, we can actually test Einstein's equation to some extent. In this talk, I shall mainly use statistics which are 2-point correlation function given by 2-point correlations, namely the 2-point correlation function determines the probability above or below the mean of having a galaxy in some space-time position Q if I know I have already one in some space-time position P. We have here the talk now about the amazing CMB data from the Planck collaboration, which has been used to determine parameters in a lambda CDM model. And we have seen that these parameters are determined now with roughly 1% precision. But there are still tensions, as Silvia explained us, like the Hubble tension. And so the question is do we have to change our cosmological model, or do we have to change gravity to account for unexplained things, not only in the CMB, but in cosmological data. Also, this cosmological constant, which we inferred from the expansion law, has a very, very strange value, because a cosmological constant can by no observation be distinguished from vacuum energy. And if we calculate the amplitude of vacuum energy, which we need to generate the observed cosmological constant, it is on the order of milli-electron volt, a very strange number, which we have no understanding of. Now, we are also looking at galaxies and the galaxy distribution, which has the advantage of being a three-dimensional data set. And so in principle, we can learn more from it. But for that, we must analyze it precisely and understand it precisely. The CMB had the big advantage that its fluctuations are small, and so we can use perturbation theory, which is usually quite simple. Galaxies are objects formed by nonlinear clustering. So we have to go to very large scales if we want to recover or if we want to use perturbation theory. What people have done so far mainly was considering galaxies on some the galaxy distribution on some spatial hypersurface of more or less constant time, and then calculate the power spectrum of this galaxy distribution. And they have seen the so-called acoustic peaks, these little bumps here. They are, of course, much smaller than the acoustic peaks in the CMB, because the baryons are only a small fraction of the total matter. Baryons are less than 20% of the matter, so these power spectra are dominated by dark matter and not by baryons, and so these peaks are very small. But they have been detected at very high significance, and there is no doubt about it. However, if we want to make very large surveys, then we have to take into account that all our observations are never made on an equal time hypersurface, but on our past light cone. And also this past light cone is perturbed by fluctuations, right? Because there are fluctuations in the geometry. More precisely, what we actually measure are two angles, namely the direction to a galaxy and its redshift. And we have to think about how these quantities are perturbed. For example, the measured redshift is perturbed by peculiar velocities and by the gravitational potential. Also, the volume which we observe is distorted by the geometry and by lensing. The angles we look into are not the angles in which photons have been emitted, but they have been deflected by gravitational lensing. For small catalogs, for low redshifts, all of these effects are not so important. But once we go to high redshifts of order unity and above, this will become relevant, and we will see that this is not only a curse making the analysis more difficult, but it's also a blessing, because the galaxy distribution actually contains more information than just about the density of galaxies. Cosmological distances, as you know, the co-moving distance is given by the integral of the inverse of the Hubble constant, and it is model dependent. Whenever we measure distances in cosmology, we have assumed a cosmological model. At very small redshifts, all the distances, angular distance, luminosity distance, co-moving distance, are proportional to c over h naught. And this model dependence in h naught, we have taken it into account by measuring distances in h inverse megaparsec in cosmology, where h is the uncertainty of the Hubble constant. So that's taken into account. But once we go to redshifts of order unity, the matter content, the dark energy here modeled simply as lambda or curvature become very important. So whenever we convert a measured redshift and a measured angle into a length scale, we make assumption about the underlying cosmology. Here just an example, a measured galaxy correlation function with the acoustic bump here. If we convert it from angle into radial distances, and then the result will depend on the cosmology. Here, because the assumed cosmology contained omega matter of 0.24, and if one does it wrong, this acoustic peak will be at some different position. Very large-scale galaxy surveys have to be considered at first, have been considered at first order in perturbation theory by several people mentioned here. And if one thinks about it, what one really measures is, as I said, two angles and a redshift, or a direction and a redshift, and some other information about the galaxy. And then one can build the following fluctuation variable, which vanishes in a perfectly homogeneous and isotropic universe, which is the number of galaxies in some direction n, in some small solid angle and small redshift bin, minus the mean of all the galaxies in this redshift bin, and divided by the mean. This quantity is gauge invariant in first order. It's directly measurable, and therefore it must be gauge invariant. And we can determine its correlation function, which will be a function of two redshifts, where these two quantities over densities are measured, or under densities, and the angle between the two directions. Putting density and volume fluctuations and really calculating how photon geodesics in first order, one can calculate this quantity exactly in terms of gauge invariant quantities like the Bodine potential, the velocity in longitudinal gauge, the density fluctuation in constant curvature gauge, etc. So this is a gauge invariant expression. And there are the most important terms in it are the density fluctuation, which is the first term, then the so-called redshift space distortions. This is in green here, and the Doppler term, and a so-called lensing term or lensing magnification, which is this pink term here. There is, I forgot the factor B in front of the density I see here, the bias factor. But what is an important quantity is this S of C, which is the luminosity bias, which is the magnification bias, which comes from the fact, you see this magnification term actually has two portions, this factor 2 here, and then a minus 5S here. And the first factor comes from lensing. If I have an overdensity in front of me and I look left and right, then actually the light rays are bent towards me. So I imagine these two overdensities to be further apart. So I increase the angular volume between the two directions, which means that I increase the volume, so I decrease the density. This is this minus sign here. On the other hand, if I have lensing convergence, galaxies which would have been too faint to make it in my survey, let's assume I have really a magnitude limited survey, they might be they might get increase in magnitude due to lensing, so that I actually can see them and that they are part of my survey. This is this factor 5S. S is just, this 5S is just the logarithmic derivative of the luminosity of objects, or sorry, of the flux of objects at the limiting magnitude of my survey. So this is a survey dependent quantity, but it can be measured in each survey. It's important to include it. So here, for example, redshift space distortions, these are these redshift space distortions which I talked about. They come from the fact that if I have overdensity somewhere, then galaxies behind that overdensity may flow into the overdensity. So if I interpret their position, the redshift actually is lowered by that, and therefore I consider them to be closer than what they actually are, whereas galaxies in front of the overdensity also flow more away from me, and I consider them further away than they actually are. This leads to this squashing on large scales. On smaller scales, there are the fingers of God, which are just the large virial velocity in virialized objects. This leads to a stretching on very small scales, the so-called fingers of God, while the linear perturbation theory gives you a squashing on very large scales. And this has been observed, for example, with the BOSS survey, but also with others before. Now we have this function delta as a function on the sphere for each redshift. So we can, again, expand it in spherical harmonics like the CMB and calculate the CLs, which now depend on two redshifts. And here I show you a plot of when both redshifts are 0.1, so very small, and the bin width, the redshift bin width is 0.01, then you see here the density term, which is shown in red, totally dominates the result. Redshift space distortions are quite small because the bin width is relatively large, and so they are kind of smeared out. However, if I go to higher redshift, here I exaggerate, I go to redshift 3 and choose a rather wide bin width. So again, redshift space distortions are very small if I have wide bin widths. But suddenly this lensing term I was talking about becomes very significant. And actually, if I even dominates on large scales and is of the level of 20–30% on intermediate scales. I can also look at the radial power spectrum. So I fix L and Z and look at this spectrum as a function of C prime. There, the standard terms containing only density and redshift space distortions at small redshift, Z is here 0.1, dominate, and I just see more or less the correlation function which passes through 0 at the distance which corresponds to roughly 140 megaparsecs. At higher redshifts, the lensing term comes up, as you see, and actually it changes sign. The lensing term at relatively low redshifts is negative because it is dominated by the correlation between density and lensing magnification, and this correlation is negative. While at high redshift, it's the lensing-lensing correlation which is positive, which dominates the lensing signal. Okay, so this was just a little analysis of how this power spectrum looks. How can we use it to learn something or to test even general relativity with it? One thing which we observed is if we correlate faraway bins, Z being larger than Z prime, then the main contribution from faraway bins actually comes from correlating the lensing term with density. The lensing term is given by the lensing convergence times this factor 2, which comes from the volume change, from the increase in the volume. These kappa and delta are anti-correlated. So the kappa delta correlation is always negative. And then there is this -5s, which depends on the survey. Here I show if we correlate bin 1 with itself, we are dominated by the local term, which is blue, in blue and dashed. Whereas if we correlate bin 1 with bin 4, the non-local terms, the lensing term is very important to get to the full result. If we correlate bin 1 with bin 10, these are different redshift bins, of course, then we actually find that the local term is completely irrelevant, that we are totally dominated by the correlation with lensing. So can we use this to measure the lensing potential? we have in this analysis just multiplied the lensing term with some factor beta and looked whether we can determine beta with some Fisher matrix analysis where we take into account all kinds of parameters. I just show a couple of them. And in this relation, you see if one correlates only autocorrelations, that's the solid lines, if one the dashed lines, and if one includes also cross correlations between different bins, that's the solid line. 5-bin configurations in red, 10-bin configuration in black. You see for neutrino mass, H naught, amplitude of perturbations, whether I consider only autocorrelation or also cross correlation is not so important, at least not in the 10-bin configuration. But to configure 10 bins is much better than to consider only 5 bins. For beta, it's the other way around. If I consider only autocorrelations, I cannot constrain beta very well. But the moment I start to consider cross correlations, whether I have 5 or 10 bins doesn't matter so much. But I can measure this beta with a good accuracy of a few percent, like the other parameters. And of course,
5 minutes, Ruth? 5 minutes?
Sorry?
5 minutes.
Yeah. Okay. And of course, GR would request beta to be 1. Another thing is if one neglects the lensing term, what so far all data analysis of large-scale structure have done, if one would do that with data similar to the ones which we will get from Euclid, one would bias the cosmological parameters. For example, here in an analysis without lensing, you get a non-zero neutrino mass at very high, or a neutrino mass which is larger than the one which you have inserted in the simulation by very high significance. So clearly or you get a completely wrong amplitude of fluctuations. So to measure the cosmological parameters correctly is very important to include this lensing in the analysis. This is for the photometric survey of Euclid, but also measuring the growth rate. If we want to measure the growth rate of perturbations, this is very sensitive to the theory of gravity or to the form of dark energy. A cosmological constant actually is the only form of dark energy which exhibits absolutely no clustering. On the other hand, to have a good measure of redshift space distortion, we need a spectroscopic survey. So we need to have very precise redshift measurements. And for spectroscopic surveys, actually lensing is not very important, usually. Let me not go into details. How here you see a comparison. Left, we have LSST, which will be a photometric survey. Without including lensing, one has the red contours. With including lensing, one has the blue contours. So we see they shrink considerably, especially the amplitude can be distinguished from bias only if we include lensing in a photometric survey. In a spectroscopic survey, including or not lensing is not such a big deal because the degeneracy between amplitude of perturbations and the galaxy bias is already broken by redshift space distortions, which are well measured. However, if we want to measure the growth function, here it's the growth function times sigma 8, because that's what we really can measure directly from redshift space distortions. Including or not lensing is very important. Including lensing with the power spectrum is complicated and it's not straightforward. So here we use the correlation function. We use the code for the Fourier relativistic correlation function. And the difference between including and not including lensing in the growth factor is shown here. And the errors with which we expect to measure this from Euclid in these different bins is also no, that's actually, sorry, it's for SKA2, so very futuristic, the square kilometer array with galaxy number counts in its full extent. And here we see actually that the error which we make divided by the statistical error of the survey can become very large. So here, this means the error which we make in this bin, if we neglect lensing, is about 2 standard deviations. Here it is about 1 standard deviation, here it is a half, and above that's lower redshifts. We could say, okay, we can accept it. While at these high redshifts, which are very important, one makes a really significant error in the growth rate and will then conclude that there must be either some early dark energy or there must be some deviations from general relativity if one does not include lensing. Yeah, I wanted to say some words about EG statistics. It's an interesting idea. It's a quantity, namely the ratio between the lensing density correlation divided by the density correlation. One can show that these should be independent of scale. And so one should be able in general relativity, but probably not in any other theory of gravity. However, when we measure density, we don't only measure density, but it also has the lensing term. And if one does not consistently subtract this lensing term, this can lead to systematic errors, which I show here. We have calculated these errors for the DES survey, something DES-like. There it is only a few %, as you see here, so it's not so important. However, if we have a survey similar to Euclid, then at redshift 2, it becomes like 40–30%. At redshift 1.5, it's on the level of 10%. Whereas at redshift 1, it is nearly 0. And that is comes from the fact that this lensing convergence, magnification completely vanishes if S is 0.4. And for Euclid, by chance, at redshift 1, S is very close to 0.4. What one can also do to get rid of this lensing magnification is intensity mapping. There one measures really surface brightness, which is not affected by lensing, and therefore one does not have this correction. If one applies the correction, one finds a really scale independent E of G, as you see here in the lower panel. Yeah, this is all. I just want to conclude. What I want to say is that if we measure cosmological data, cosmological large-scale structure data with power spectrum or theta of R, they always need an input cosmology to convert redshifts and angles into length scale. And we have to consistently take that into account, especially for parameter estimation, because also this conversion depends on parameters. Furthermore, it's not evident how to include lensing in these surveys. For large, precise galaxy catalogs, which we will have in the future, we will be able to measure 3D correlation functions and spectra directly in angular and redshift space, where the theory is very simple. These quantities, they have more variables, they are more noisy, but they also contain more information, as we said. They contain information about the matter distribution, the density, about the velocity via the redshift space distortions, and about the geometry of space-time via lensing. We can therefore, in principle, determine both the components of the energy momentum tensor and the geometry, which would, in principle, allow us to test Einstein's equation. Especially the correlation between convergence and the galaxy overdensities are very suitable to test GR via, for example, the EEG statistics. Not only the spectra, but also the bispectra depend sensitively and in several different ways on the theory of gravity, the growth factor, the relation between the two Bardeen potentials, etc., etc. So we hope that this is a new route, not only to estimate cosmological parameters precisely, but also to test general relativity on cosmological scales. Thank you.
Thank you so much, Ruth. Interesting talk. So let's see if there are questions. So if you have any question, please type your question in the Q&A part. Okay, so before anyone asks, maybe I can ask one question myself. So Ruth, can you give some comments on using peculiar velocities to measure the growth and which might be eventually used, and how they can be competitive with the redshift distortion?
To measure peculiar velocities in another way than via redshift space distortions?
No. I mean, using peculiar velocities to measure the growth rate, of a structure, okay. Because I think, yeah.
Yeah, so I didn't enter into any details here. So the way you do it is, if you look at the correlation function, which we did here in this work, the correlation function, as also the power spectrum, correlation function has a monopole and a quadrupole. A quadrupole meaning it depends on the direction in which you look. So the redshift space distortions actually add a quadrupole term to the correlation function. As you have seen with this image here, this depends on this. If I would have here a totally spherical overdensity, it looks totally squashed. So the fact that there are peculiar velocities which lead to redshift space distortions breaks the isotropy of the correlation function. It makes it different in transverse and in radial direction. And that gives in the correlation function a quadrupole. And this quadrupole actually helps you to measure, since the velocity in GR is given by the density via Newtonian gravitational acceleration. So you can show that F, which is the logarithmic derivative of the density fluctuation with respect to redshift, times the density is equal to the velocity in GR and if you have non-relativistic particles. So you can measure this F by measuring the anisotropy, the prefactor of this anisotropic term of this second Legendre polynomial in the correlation function. And that's what we have done. And then you have the square of it also, which enters, which gives you then a kind of fourth order polynomial. In total, the correlation function becomes a fourth order polynomial in the angle between the direction you look at and the radial direction. And by determining the coefficients of this polynomial, you can determine F, which is this growth rate defined here. So that's what Euclid will do. It's one of the main goals of the Euclid spectroscopic surveys, to measure this F. And Euclid will not be able to measure it as well as we have as these measurements here. Here we have taken SKA, which will measure it better.
Okay, so any question still I'm looking for? So, okay, maybe I can ask one more question. Since I have time, I'm using the opportunity of being the chair. So SKA, we have to wait 10, 15 years, right? So do you think there is a hope that in this decade, we might find something beyond GR, or what you yourself think about GR? Do you think that it will survive, or we will basically rule it out?
Of course, I don't know. whether it will survive. I mean, it's a very beautiful theory, of course. I like it very much, as probably all of us. But on the other hand, I think this discovery of dark energy is something so weird that we are all asking ourselves whether something else goes on. What exactly? I'm open. I don't know, honestly speaking, what really goes on. But I'm sure that the cosmological constant is not the last word. Yeah. There, I'm quite convinced.
Okay, let's hope to have some very exciting things in the few years come, because Euclid and DESI started actually getting light, you know, and actually we are trying to be earlier than Euclid, you know.
No, I also think that, for example, DESI will be able to measure, for example, the lensing term. We'll see the lensing term also in its survey, and Euclid for sure will see it. So.
Sure. Yeah.
That will already be a test. For example, we measure now the shear with weak lensing surveys, and we can measure the convergence with galaxy number counts, and these power spectra in GR, they should agree, right? In lambda CDM, these power spectra should agree. However, if we have something else, then they typically might not agree. So that will already be a test.
So let's wait and see what would happen. Okay, so looks like that there is not much questions. Here in Korea, we are basically like at 7 o'clock in the evening. Anyway, thank you so much, Ruth, for the great talk, and hope to see you in person in Korea and East Asia. So yeah, thank you very much. So I think we can finish this session now, and see you, some of you, tomorrow. Okay, thank you so much.